Earth, water, fire, and air, the four essentials. Four building blocks from which some ancient Greeks imagined it was possible to make everything, including this opening sequence. Subtitling by Since then, 2,000 years have passed and we've discovered atoms. There are literally atoms everywhere and in quantities we absolutely cannot imagine. An average adult human contains something like 7 octillion atoms, a staggeringly huge number, which is 10,000 times greater than the number of stars in the observable universe. Yet, in nature, we've discovered 118 atoms, 94 of which occur naturally all arranged in this table, which is the coolest in the universe, since it actually contains almost all the matter in the universe. All matter, including us, is made from just about 100 types of atoms. Which really isn't a lot when you think about the fact that by arranging these 94 blocks you can make anything and everything. You, me, this landscape, the Earth, almost all the matter in the universe. But then, a little problem appears. If these things make everything, what made them? In the second episode of this series, we left, after the Big Bang, a universe that was too cold to create new elements, and which, as if out of breath, had only produced hydrogen, helium, and a pinch of lithium. All in all, nature had only checked 3 boxes. So, how did we go from that to this? From this to that? Under? Part of the answer is found in the sky, because the stars, not only bringing light, will also transform matter there. To understand how, let's head toward the heart of one of them. At random, our sun. Here, at the heart of this infernal furnace, heated to 15 million degrees. The nuclei of hydrogen atoms collide with such force that they end up fusing to form helium, releasing in the process a colossal amount of energy. This ensures the star's balance between its gravity, which tends to make it collapse under its own weight, and the pressure generated by the energy released from fusion, which opposes it. All the reactions that take place there come at the cost of converting mass into energy. To shine, a star doesn't burn, it fuses. In the sun, 600 million tons of hydrogen become 596 million tons of helium each second, with the rest turning into energy. A mass equal to the pyramid of Khufu is destroyed there, and this has continued non-stop for 4.5 billion years. That's the cost of turning the universe's simplest atom into something slightly more complex. For the Sun, in 5 billion years, when this fuel in the core is almost exhausted, gravity will take over again and the star will contract slightly. The temperature at the center will rise, reaching 100 million degrees. At that moment, our star will switch its fuel. The helium atoms will then be able to fuse to form carbon, nitrogen, and oxygen, releasing a large amount of energy, so that the temperatures in the layers surrounding the core will become high enough for them to fuse in turn. Subtitles 501. These drifting clusters of matter are both the signature of the agony of a star shedding its veils, but most importantly, the promise of an environment enriched with 2 new elements, carbon and nitrogen, which may one day end up seeding in their turn clouds from which other stars will form. Clouds that could collapse to form stars larger than ours. 501 were over millennia inside these aging stars' swollen interiors. A strange process that allows the transformation of certain atoms into others when high-energy particles penetrate their nuclei. And this is how many other elements make their appearance in the universe. They can be propelled into space by solar eruptions, stellar winds, or eventually drift into planetary nebulae. Suddenly, things start to get better, but our picture still has far too many gaps for us to be here. Because even if we focus, among the 29 elements used by living things, only on the 6 atoms that are unanimously found in all living things, and which are called the carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur group. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Oops, still no hops. To understand why, let's take the example of oxygen. In fact, even though these stars make large amounts of it in their cores, producing an atom doesn't necessarily mean sharing it. At the end of its life, half of the sun's matter will be ejected into space, and the other half will end up trapped forever in a star forming in place of the vanished star, a white dwarf that will contain almost all of the oxygen forged by our sun. In other words, no one will ever breathe oxygen produced by this type of star, since the amounts released into space by them are negligible. And since the Schnapps gang makes up nearly 99% of the atoms that make you up, we can say that the past of half of them doesn't mean being half alive. In reality, all the stars whose mass is less than 8 times that of our Sun, which make up 96% of those we see in the sky, really only check a few boxes on the table, because a large part of what they produced ends up trapped forever in a bare core. Not a single gram of iron will be forged there, and if you're missing that box, that's a problem. Because iron is used, among other things, in hemoglobin, which carries the oxygen that still doesn't exist because it hasn't been shared. Fortunately for us, white dwarfs, although they are prisons that lock up many boxes, can, as a side effect, be a source of complexity. If one of them forms in a binary system and has as a close companion a star turning into a red giant, it can then start to siphon off the outer layers of its massive neighbor. The transfer of matter between the two stars will increase the mass of the smaller one, forming a disk around it that speeds up before plunging in. The process may take hundreds of thousands of years, but when the white dwarf reaches a critical mass, a chain nuclear reaction occurs, leading to the collapse and then the complete disintegration of the white dwarf, usually tearing the system apart. The violence of this explosion, called a Type Ia supernova, is such that, for several weeks, a single star can become brighter than all the other stars in its galaxy combined. In a fraction of a second, the phenomenal energy released by the explosion will allow nearly half of the table to be filled, while ejecting these dozens of new elements out of the system at tremendous speeds. And here is the surrounding space. Contains potassium for nerves, calcium for teeth and bones, and cobalt for vitamin B12, copper and vanadium to keep our enzymes running smoothly, or even zinc, which stabilizes them and helps oxidize alcohol. But paradoxically, still not a single atom of oxygen, because all those present in the core of the little star were transformed into other elements during the event. And here we are again with a table that still has far too many gaps, and so still no us. In fact, even if some of these elements make up only a tiny part of us, just missing one box can instantly cause you serious trouble or death. Without sodium, there's no transmission of nerve impulses. Without magnesium, no muscle contraction. Having half the chart doesn't mean you're half alive. Luckily for us, giant stars exist that are at least 8 times heavier than our Sun. They represent only 4% of those found in the sky, yet we owe them almost everything. In these giants of space, the temperatures are high enough that at the end of their lives, fusion is organized like an onion, with the giant star fusing heavier and heavier atoms as you get closer to its center. In the layers of these stars, blocks of matter are created up to the most stable element in the universe, iron. And from that point, everything stops, because iron is a barrier that refuses to fuse. The star must do the same to break through, because from the moment iron becomes predominant in the core, the energy produced there is no longer enough to counterbalance the pressure exerted by the outer layers. The contraction of the core can no longer generate the energy needed to maintain balance. And in just a few milliseconds, the core of the star collapses in on itself, dragging the outer layers down with it as they plunge toward the center at speeds close to the speed of light. And these layers crash into, then bounce off, a compressed iron core about 10 kilometers in diameter with a temperature reaching 1 billion degrees. In this inferno, the iron atoms are subjected to such pressure that their components are almost instantly transformed into neutrons, which then overwhelm the surrounding atoms, turning them into others. The phenomenal amount of energy released then causes the star to explode, ending its life in a blaze, producing in a fraction of a second almost all the missing atoms in the table. The star has given its life there, drifting off into space, carrying new elements with it. You can finally relax, take a breath, and start to breathe. These gas filaments are a breath of fresh air. You'll find oxygen, magnesium, sodium, or iron there. The vast majority, if not all, of these elements that we find on Earth were once at the heart of one of these cataclysmic explosions. Think about it the next time you use a sheet of aluminum. All that metal was made by this kind of explosion. And if we set aside the tiny amounts expelled by stars with less than 8 solar masses, almost all of the oxygen present on Earth also had to go through a supernova of this kind. These fiery deaths of stars are common. It's estimated that, on average, 2 supernovas explode per century in our Milky Way. The traces of these past explosions are scattered across the sky, where they are visible through our telescopes for thousands of years. Here, the remains of matter that were torn away are revealed by the expanding shock waves, which crash into the surrounding material at several thousand kilometers per second, heating it to temperatures close to those at the center of the Sun. There, somewhere near the center of this image, a star died about 10,000 years ago. In the wisps of drifting matter are atoms that did not exist before. In fact, even before exploding, massive stars can eject into space some of the material that makes up their outer layers. The star located here will one day turn into a supernova. In the meantime, these convulsions feed the cosmos with ashes rich in new atoms. Soon this bubble of gas drifting through space at over 1,400 kilometers per second may go on to disturb clouds of interstellar gas, to the point of eventually triggering in one of them the formation of other stars whose swirls will in turn carry on the cycle over several generations. A cycle of deaths and ignitions began about 100 million years after the Big Bang, with the universe's first stars. Stars that had nothing but hydrogen to consume and were the first to transform matter. Since then, each new generation of stars has contained more heavy elements than the last. Their metallicity, that is, the fraction of their mass that is not made up of hydrogen or helium, is therefore a very good indicator of the age and origin of stars. Thus, the most recent stars are often the richest in metals, thanks to the work of previous generations who forged in their hearts slowly while dying or in the brilliance of a sudden death. What we find here is something without which we wouldn't be here, neither you nor me nor you. It may have been around 5 billion years ago. The explosion of a giant star nearby may have enriched and disturbed a cloud of gas, thus helping to ignite our sun and form a few planets in its wake. And, on one of them, humans taking a deep breath of the universe before watching a new star appear in the sky. What were your great-great-great-grandparents doing? He was burning things to turn them into something else. He was having a great time. I didn't know them. They lived in the sky and died a long time ago. That was billions of years ago. We are web creators aiming to make this our job. Support us by tipping through the join button or buying us a coffee. No, but it's awful. Who wrote that? I think it was me, so I'll just say it's fine.